call a radical equation or a root equation, and there's a set of steps to solve them, just like with quadratics. There's a set of steps. Here there's a set of steps. Step number 1, isolate the radical. Get the radical by itself. That's already done. Second step, square both sides of the equation. Okay, so if I square the left side, square the right side, we get x here, and over here, we actually have to FOIL that out. Like, we don't have a choice. We have to FOIL it, so it's x squared minus 4x plus 4. That's what we get if we did that times itself. And then it's now a quadratic, so you move everything over to one side. It becomes x squared minus 5x plus 4, because you subtracted x on both sides. And does that factor? Yes. It factors to be minus 4 minus 1. And that gives you two solutions, 4 and 1. So which one is it? It's 4, right?
Yes, this was for the blue and the red.
It was for the blue and the red.
Yes, 4.
What about the 1, though? So, do you remember this step right here? Where we squared both sides of the equation? Anytime you square both sides of an equation, you introduce the possibility of what are called extraneous solutions, which means you introduce the possibility of getting answers that are actually not answers. So anytime you solve radical equations, you are supposed to check your solutions to see if they work. So when you come back and you look at this, if I plug 4 into this, does it work? 4 square root of 4 is 2. 4 minus 2 is 2. 2 equals 2. Yep. But what if I plug in 1? 1 square root of 1 is 1. What's 1 minus 2? Negative 1. Right? That doesn't work. The reason why we got this answer is because when we square both sides, we actually eliminate that possibility of having one side be positive and the other be negative. We've eliminated that because anytime you square something, you make everything positive, right? So just remember that. Anytime you raise both sides of an equation to an even power, whether it be squaring it, raising it to the 4th power, 6th power, you introduce the possibility of extraneous solutions, so you're supposed to check your answers. So we could tell visually that the 1 wasn't going to work, it was going to be the 4, but that's just explaining why. So 4, there we go. All right. Yes?
It's because the square root of x is like a sideways parabola, so there's like a kind of like a phantom thing. It's pointing at the left side.
Yeah, it's actually trying to find like this one down here. Yeah. So if that was the full parabola, then we would actually have two x-point intersections.
Would that be where imaginary numbers come in?
Not in this case, no. No, because it's actually, there's a way to define that so that the parabola goes the other side. Or so it would look like a parabola. All right, here we go. Let's set up the integrals. We have one integral. The first one, let's call this one right here. Okay, we'll call that region 1. We'll call this one region 2. All right? So for region 1, the integral is going to go from 0 to 2, and it's going to be the top function minus the bottom function, right? The top minus the bottom. What's the top one here? Blue, which is square root of x. What's the bottom one? The green, which is 0. So this is just going to be root x minus 0. I don't need to write minus 0, but I'm just doing it to stress again the top minus the bottom. Yes?
The 4, that's not, that's for the blue, the red and the blue, right? You're just
Yep.
dotted line to show it's on the...
Yeah, I set these two equal to one another here.
Okay.
The red and the blue, set them equal, and that tells me the x values where they hit each other. Does everyone understand this is the integral for the area of the region 1? Yeah? And then for region 2, the integral goes from 2 to 4, right? The top function there is the square root of x. What's the bottom function?
X minus 2.
So I'm supposed to subtract that, right? I'm supposed to subtract, be real careful here, x minus 2. Top function minus bottom function. In parentheses, you have to have parentheses because that negative would have to distribute through. And do y'all feel like y'all could do those and get numerical values for each of those? Yeah? I leave it to you, all right, that you could work those out the rest of the way. And then our final answer is those two answers added up, right? Those two together. You could, if you want, and actually this is probably preferable to do it this way, is just to write it all as one integral. Just to write it all as, you know, the area of the whole thing is the integral from 0 to 2 of the square root of x dx plus the integral from 2 to 4 of the square root of x minus 2, that quantity dx. Like that's all of it together, right? It's that one plus that one. Add those two up. Any questions?
So when you chose the first region, that was the only space you could do that. You couldn't really do that anywhere else because it's not bounded, right?
Wait, the what?
So like the region 1 was the blue and the green.
Mm-hmm.
And that's the only region you could pick for solving for that because it's enclosed, right?
Well, I needed to see where so no matter where I am in this region, the blue is always the top one, right? The reason that I stopped at 2 is because I wanted to know where does the bottom function change? Like here it's the green and then here it changes to the red.
Oh, okay.
Right? So I'm looking at where that change occurred on my bottom function. That's what dictated where I cut it.
Okay, that makes sense.
Yeah? Okay, let's see what our next one is. Same problem. It's the same problem, right? So this is not a typo, all right? That's the problem we just did, example 2. And now we're looking at example 3 is the same thing. So I need to now have you reconsider something that maybe you did in college algebra, consider this. I really want to make sure that we can kind of like stir all that up again so we can handle this problem in a different manner. I don't know how deep I want to go into this though, so let's just have a little discussion. See how this goes. If I put this on the board and I draw that and I ask you, is that a function? What would you say? Is that a function? Most of you are going to say yes, right? Because why? It passes the vertical line test, right? Which means that any vertical line I draw, I don't hit the graph more than one time. If I draw this, you tell me, if I ask you, is that a function, what would you say? No, because you draw a vertical line, it hits it more than one time, right? So that's where most of us are comfortable with that concept. But there's actually more to it than that. This right here is not a function of x. Okay? It's not a function, this is a function of x. Scratch what I said. This is a function of x because it passes the vertical line test, right? This is not a function of x because it fails the vertical line test. So I'm going to put here function of x, yes. Function of x, no, right? Now, what do we mean? We mean that if you plug in a value of x here, don't care where you plug it in, there's only one output here, right? It doesn't matter what x you pick, you're going to have one output. X, one output. x over here, one output, right? Does that happen over here? If I plug in an x, I actually have that output, that output, that output. That can't be a function of x then, because that means that if I plug in a number, you have three things come out. And that's, functions don't behave that way. Functions is one thing in, one thing out, right? So I would say here, this fails to be a function of x because if I plug in an x, I get multiple values of y. Here, if I plug in a single value of x, I do get a single value of y. But what about if I ask the question the other way around? Is this a function of y?
No.
Or same question there. So is this a function of y? Meaning if I plug in a value of y, let's say I plug in a value of y. How about right here? If I plug in that value of y, do I have a single value of x corresponding to it? Yes, but not everywhere, right? If I plug this value of y in, I have that x, and that x. I have three different x's. So I can't say here that if I plug in a y, I'm going to get one value of x out. Here, if I plug in a y, I'm going to get three values of x out. So this would not be a function of y. It is a function of x, but not a function of y. It's like looking at it reversed. And then what about over here? That one is a function of y, right? That is a function of y. Because if I plug in a value of y, no matter where I go, I'm only getting one value of x corresponding to it. So a function of y, yes. Okay.
So if it's a function of y, it basically has to have a horizontal line test?
Okay, exactly. So another way we could recap this is, if you look at the graph of some relationship, if it passes the vertical line test, then it's a function of x. If it passes the horizontal line test, then it's a function of y, right? So this is a function of x, but not a function of y. This is not a function of x, but it is a function of y. Is that what you were asking?
Yeah.
Yeah. So
Doesn't the horizontal line test also do?
that's inverses, right? So we want to distinguish the two, because you said, couldn't we just do that? I said, yes, you could look at it that way. So with the horizontal line test, the horizontal line test is how you check for inverses, but the condition is that you have to start with a function in order to begin to talk about its inverse. Okay, what about this? One last one, hold on. What about this picture? How about just a circle? Is that a function
A y index?
of y? Is it a function of x? No. Is it a function of y? No, it's a function of neither, right? So you don't have to have one or the other. You could have curves that are neither functions of x nor y, right? So now if we take a step back to my first question when we first started, so when I drew this on the board, if I put that on the board and I say, is this a function? Your answer should now be, well, or you should state in your answer, yes, it is a function of x, but you shouldn't say just it's a function because there's more to it than that, right? Okay. Now, why is this important? Well, because what we can do now is we can look at everything we've been doing. I'm just going to draw it before I actually show you the note. What if we have something that looks like this, and we want to try and find the area? So let's say I have my x and y axis here. And let's say somebody gives me a curve like this, and now that is not a function of x, right? And then they give me some other curve, let's say like this, that is not a function of x either, right? Those are both functions of y, not x. And what if I want to know the area of this region? Well, you cannot do vertical rectangles. You cannot. Because if you try and draw a vertical rectangle in here, let me just imagine a vertical rectangle right in here like that. If you try that vertical rectangle, what's the top function? Well, it's not a function, but what's the top curve? The red one, right? What's the bottom? The red. How can the red be both the top and the bottom, right? They have to be different, right? In order for you to, because if you subtract the same function from itself, you get 0, right? So it doesn't make any sense for us to do a vertical rectangle. However, if we draw our rectangles this way, now instead of thinking about a top and a bottom of a rectangle, we can think about like a right side and a left side. And do you see that the right side would be the blue and the left side would be the red? And no matter where I move here, if I put my rectangle down here, it's still the blue on the right, red on the left. If I go up here, still blue on the right, red on the left. Got it? And so what we're going to do is we're going to just change our perspective from vertical rectangles to horizontal rectangles, and then that's going to change our formula a little bit. Because instead of going from, let me draw the picture over here for you. Instead of having this picture where we went, here's f on top, right? I'm going to put it like this, f of x, because that is a function of x, right? And then on the bottom we have some function g of x. Instead of drawing this rectangle and then saying that this side is f of x minus g of x, and the width of this is dx, we're going to switch everything, rotate everything 90 degrees, and we're going to have this. The rectangle goes this way. This right here is not f of x, it's some function of y, right? Not a function of x, a function of y. And then this one right here, g, is some function of y, right? Oh, I forgot something over here, I apologize. This went from a to b, right? Where they hit each other. And we do our integral from that. Over here, we're going to, well, I'll get to that in a second. What would this rectangle's area be? Let's talk about the area of this thing. So how long would this side be? F of y minus g of y. How thick would this be? D, what's changing? So, yeah, so over here, when we're moving back and forth, the thickness of that rectangle, right, is dx because it's our little infinitesimal change in x. Here, if we're moving our rectangle up and down like this, then our changes are occurring in the y value, right? So that's going to be dy instead of dx, right? And so our integral should be this times that. That's our areas, the areas of each of those, right? It should be this length times this width, that times that, boom, boom. From where to where? This point to this point, right? It's where they hit each other on the y values. So we don't call it A and B, so we don't confuse it with that. We call it C and D. So C to D. This is all going to be formally put up in your notes right now, but just wanted to kind of motivate the idea.
So it's not really different, just the values are changing?
We have to be working with functions of y and not x, right? They have to be functions of y, not x. Was there a question?
Yeah, so if you had a complicated shape that you were trying to carve up in the pieces,
Yeah.
can you mix and match?
Oh, yeah.
Say like this section's x.
This section, I'm going to do it with vertical rectangles. This section, I'm going to do it with horizontal. You can carve it up however you want. Let me put the formal note up there. I see your hand. Hold on a second, though. Let me get the formal note up here. So here's basically everything I just said, right? Horizontal rectangles, we are talking about functions of y, not functions of x. Okay? Remember how earlier I said that the f of x had to be above the g of x, like the f was on top, g was on bottom? Here, for functions of y, the ones on the right are the same as what the top used to be. So the ones to the right are bigger than the ones to the left, which is why in the picture here, notice in the picture here, the f function, f of y is the one on the right side, the g of y is the one on the left. And then you find a formula for that rectangle, right? This is what I just drew. dy instead of dx, and then your formula is almost exactly the same, right? Now let's see if we actually understand this. You want to ask your question while I'm getting to this?
Is a circle a function of like anything at all in any
You can represent a circle as a function, but you have to use parametric equations. You can do it with parametric equations, which we will actually talk about at some point. Yeah, there is a way to represent a circle as a function.
Is it fair to say that everything is ultimately a function in some way?
I think as long as it's figured out, but
Right, I mean, like, any equation is gonna make a function, it just might not be defined.
would a circle be defined functions or functions?
That you can't. Not every relationship can be defined as well. That's a really abstract statement. I mean, because then if you're saying function, then you're not restricting yourself to like the functions we're talking about here. We're talking about functions in general, right? In general, like what is a function? You know, functions don't have to take numbers in and spit numbers out. Functions can take other things in and spit other things out. So it's, I think that's, yeah, that, I don't, yeah. Hold the, time out.
Yeah.
Time out. Let's do this one, all right? All right, so this is the same problem we had earlier, right? Same problem we had earlier. And I said, oh, maybe I made a mistake, a typo here.
So it doesn't change the way the graph is drawn at all?
Nope. It's the same exact problem, right?
I think it makes it easier.
But you know how in the previous like view of this, we cut it up into two pieces because we had the idea of vertical rectangles. So we had to do two different regions, didn't we? But if we look at it in terms of horizontal rectangles instead, do you all see that the function on the right would always be the same and the function on the left would always be the same, like they'd never change? I'm not sure why that looks like that. Let me bring this one, yeah. Okay, so imagine horizontal rectangles in here. If I drew a horizontal rectangle right here, the blue's on the right, the red's on the left, right? It doesn't matter where I draw these. Blue on the right, red on the left. Blue on the right, red on the left. No matter where I go, right? Even down here.
So that third, the y equals 0 doesn't matter in this.
Yeah, you don't have to consider it, I don't think.
We still need it to define the region, because if we don't say y equals 0, then again, this just floods out into this. But what it will do is give me my limit of integration. My rectangles are going to start down here at 0, and they're going to stop when I get up here, right? Because I'm no longer going left and right. I'm not doing this with vertical rectangles. I'm doing it with horizontal. Do y'all see how the idea of treating this with horizontal rectangles is slightly better than doing the vertical, because you're not going to have to break it into two. You're just going to do one integral. Now there is, yes?
So with like us treating these or using the horizontal rectangles, then would we have to then like I guess switch the equation?
Yeah, so right now we were given equations, and that was exactly what I was about to put up here. This is the equation. This was y equals, I forgot. This was the square root of x. I think my colors are opposite of what I had earlier. X minus 2, right? Those were the two equations? Yes? Notice that both of these equations are solved for y, right? They're solved for y. You get y equals this, y equals that. Whenever you have an equation solved for y, then the other side is actually your function of x, right? You could, if we wanted to, rewrite this f of x equals x squared, right? I could write it that way?
Yeah.
Okay, we don't want that though. We want these to be functions of y, which means instead of having these things solved for solved for y, we have to solve them for x. So that has to be done if you're going to go to horizontal rectangle. So I'm going to take both of these, okay, both of these, and I'm going to solve for x. Solve for x. Okay, let's solve this one for x. Square both sides, right? Square both sides. And you get y squared equals x. Now you could write that as x equals y squared. See, x depends on y. You give me y, I give you x, right? So x is now a function of y. And then on this one, that one's even easier to solve for x. You just add 2 to both sides. So x equals y plus 2.
How do you handle the y equals 0?
Pardon?
How do you handle the y equals
The y equals 0 is not going to come into play in terms of solving anything because it's a limit of integration. Remember, these rectangles are going to start where? 0 up to 2. So that's where it comes into play. Because you can't solve y equals 0 for x. Yeah.
It's, so in order to solve for y,
Solve for x.
in order to solve for x, you have to isolate that?
Isolate x. That's what I mean when I say solve for x. You're isolating x. Just get it by itself on one side of the equation. Now, let's stick to the notation that we have here. According to the notes I just gave us, this right here, the one on the right side should be f of y, right? That's what I call it, f of y. And the one on the left is g of y. So what is f of y for us?
The x minus 2. Or sorry.
It's this one, but now I've solved for this. So f of y is? F of y is? Y plus 2. It's that right there. It's y plus 2. You solve for x, right? So now the x value is a function of y. That function of y is y plus 2. If you give me y, right, think about it. If you give me y, this will return to you the x value, right? Give me y, and it will give, like, so let's say y is 0. If y is 0, then what's x? 2. Does that match up? Right there. If y is 0, x is 2. It's just reverse of everything we've been doing. All right, then that means the g of y is the y squared, right? Now, we have this so far. Integral, it'll be the f of y, which is y plus 2. We subtract from that the g of y, which is y squared. I don't need that in parentheses. dy, that's my integral. But I need my limits of integration. I need where does it start and where does it stop. The starting is easy, I think. It's 0. We can just tell by visual inspection. But where does it stop? It looks like 2, but how do you find that? Like, you can tell by the picture. You set what equal to each other? These two equal to each other. These two, right? Because you want to know where these... You want to know the y values where they hit each other, not the x value. If you go and set these equal to each other, what are you going to get? You're going to get 4, right? And that's not what we're looking for. We're actually looking for the y value where they hit each other. So you have to set, I'll just put it right here. For the intersection, you're going to set y squared equal to y plus 2, and then we're back to another quadratic. Bring everything to one side. That actually does factor y minus 2, y plus 1. And you get 2 answers, 2 and negative 1. One of those is extraneous because we squared both sides way over here. So this right here actually thinks that this is a parabola that goes like this because we squared both sides. So our only answer that makes sense here is 2. 2, and then we could do that integral. You get the same answer doing that than you would if you did the one where we broke it into 2 pieces before. You get the same exact answer.
So,
Yeah.
for setting up your interval, like previously on the x, you know, it was we were subtracting the x minus 2, so now this one starts with the y plus 2 and subtracts.
Well, that's just because of the geometry that we see here. You always want to look at it as which one is on the right, which one is on the left. Don't be thinking about like, oh, they're just going to switch. Don't think that way. Think about when you draw it, which function's on the right, which one's on the left. The one on the right goes first, the one on the left goes second. Okay? I think it's just better than thinking it just switches, because it doesn't always have to switch. Yes.
I have a question on.
I'm not finishing this, by the way. Dot, dot, dot. You can figure out the rest of that. Okay, go ahead.
For this question, it's hard to, can you put it back up?
Oh, well, maybe. Let's see. You want that?
Yeah, yeah.
Okay.
So, if we were, like, because this is the, like, we did this before, but when y was the function, or when it was a function of
X. Uh-huh.
Like, if we were to rotate it, like, how do I put this? Like, when we do the math, how come we're not getting that space between, like, in that phantom parabola and the in that blue line?
Oh, why are we not getting this?
Yeah.
Because we understand we need to start at 0.
Oh, okay.
Right? If we actually did want this right here, then we would need to find that, which was what, -1, I believe? And then we would go from -1 up to 2, and that would give us all that, as long as we're doing horizontal rectangles.
Mathematically, how do we find that we start at 0? Because, like, when we look at the graph.
Because of what was given to us in the original problem. The y = 0 right there told us we have to start at y = 0.
Okay.
If that wasn't there, then it wouldn't be an enclosed region, right?
Yeah, I see.
Yeah. So that's a very important part of this problem, is that that has to be there.
So before we were just assuming it was there?
No. It's always been there. Y = 0 has always been here.
It was one of the. It was the third function.
It's the third. It's the third curve that we drew. And there was a question: do we need it, right? And we absolutely do need it to know what region we're talking about. Take a look at that. I'm going to go get a drink while you sit here and try and sketch that. See how much you can do without your calculator. See if you can draw that region without a calculator. I think you know what all those things look like. I don't know, maybe talk to each other. I'll be gone for just a minute.